congratulations. So this is the last talk. Last but not least. It's going to solve an important problem, right? The lithium problem.
It's certainly a new direction, so.
So Seth Koren is from the University of Chicago, right? After graduating from
Santa Barbara.
ICTP, right?
Yeah.
The University of Santa Barbara. Good. Yes, that is exciting news. Exciting problem.
Thanks very much. And yeah, thank you really to the organizers for inviting me. It's been lovely to visit, and I've had a great time meeting and chatting with everyone. And I'm excited to tell you about this work that I spent a good part of my pandemic on. There's a bunch of pieces to it, so of course I'm not going to try to do everything in this time slot. So my purpose, my goal is really just to motivate the approach that I've taken and then tell you a basic story about the phenomenology, maybe point out some interesting field theory along the way if we have time. But let me start just by reminding you about the early universe in case you, can you sort of, the previous slide is still sort of up. Can you see that?
Yes. Yeah, it's strange.
Okay. As long as it isn't too distracting.
It's like an after effect of just the projector, I think.
Oh well. Okay, the early universe. So we can see visually with photons all the way back to some 400,000 years after the Big Bang. This is the epoch of recombination when the cosmic microwave background is formed. And I probably don't have to tell you that the CMB has just been an enormous boon to cosmology and particle physics. We've just gained so much information about it, about the universe from it. Now, the setting of the lithium problem is Big Bang nuclear synthesis, the formation of the light elements a few minutes after the hot Big Bang, and this is the prior thermal phase transition before recombination. And BBN is really a remarkable theory if you haven't thought about it, in case you haven't thought about it very much. For one, it intimately involves all four of our fundamental forces, right? The story in brief is that the strong force wants to bind nucleons together into nuclei, and it has to fight against the gravitational expansion of the universe and weak decays of neutrons and the electromagnetic repulsion of protons. So really everything is involved. And furthermore, once we have the standard model and nuclear physics and we've measured the cosmic microwave background, then BBN is essentially a zero parameter theory. It's just a cross-check on how well we understand. Oh, was that someone?
No, I think it was just...
Okay, a cross-check on how well we understand all of that physics. So it's an important thing to get right. How are we doing? Well, I have some plots from this great recent review, folding in the Planck data, comparing the theoretical predictions from cosmology plus particle physics plus nuclear physics in purple with the observed abundances in yellow. And you see on the left for helium-4 with 2 protons, we do a good job. But the one that should really impress you is on the right, deuterium with 1 proton. Even though it's down at 1 part in 10 to the 5, we get it absolutely bang on. And indeed, this is another great success of precision cosmology. But there is one more observable that, together with these, to some extent, constitutes our only direct evidence for the universe far before recombination, and that's the abundance of lithium with 3 protons. And in contrast to the case of 1 or 2 protons, here the amount that's predicted from the theory is far, far greater than the amount that we go out and see in stars. Now, of course, I'm happy to talk about systematics and things later if you'd like. People have been thinking about systematics from a great many perspectives over the last 40 years since the first lithium measurements. And there's still lots of great work being done probing this in every sort of astrophysical observational direction you could. But at least the situation at least is still murky in that direction. So I think it's well worth thinking about whether new physics could plausibly do such a thing, give such an effect. And of course, I'm not the first one to think about this. There was especially a bunch of particle physics work on this after WMAP came out in the mid-2000s. But in my opinion, all of those prior efforts struggle, if not really fail, because they don't do anything that targets lithium in particular. They want to modify the physics going on at Big Bang nucleosynthesis, often by having some extra energy injection from like decaying dark matter or something, or maybe even changing the fundamental constants that were around in the early universe. But unavoidably, no matter how much you fine-tune things, you still sort of modify everything. And especially in light of how well we understand deuterium, that's just not allowed. So I set out over the lockdown in my apartment by myself to think about whether there could be any plausible particle physics mechanism that would really modify lithium in particular and target it. And admittedly, this is somewhat of a crazy thought for a particle physicist, and indeed I thought this was going to be some fun model building exercise and I'd have to use all of these tricks that we've learned from the past 50 years of BSM physics. So I've been very surprised to find this theory quite close to the standard model. And so I'll start by, with the standard model. I'll remind you that the standard model fermions have a discrete global symmetry, a subgroup of baryon plus lepton number. And then I'll ask whether they might enjoy a discrete gauge symmetry. In particular, I'll focus on a subgroup of baryon minus lepton number. I'll write down the simplest UV completion for that, which is just the abelian Higgs, U1 broken down to this discrete subgroup. And morally speaking, that's the modification to microphysics. But the phenomenology is very rich. And where I'd like to get to keep in mind, to have in mind as I go through this, is I'll argue that cosmic strings formed during this phase transition in the early universe can have strong scale interactions which destroy 3 protons at once, turning them into positrons, and really just 3 protons, dictated by these, really the standard model symmetries. And so my story is I want Big Bang nucleosynthesis to proceed as normal, and then sometime later, whatever nuclei are around can hit these cosmic strings, and only the lithium nuclei will be disintegrated by them. So that's where I'll be going.
Talking about global discrete symmetry in non-perturbative fields, preserved non-perturbative.
Yes, yeah, anomaly free. Indeed, so perfect, I'll start there. Good, yeah. So I'm going to start by thinking about an important question about the real world that we don't think about, that we don't talk about all that much these days, which is that of proton stability. Now, our theoretical bias from these simple grand-unified theories that we learned in the 1980s is that the proton is always unstable. Okay? There's just some representative proton decay diagram. And this was great news in the 1980s because it meant that we could build these enormous, fantastic detectors to try to look for proton decay and gain low-energy access to this very UV physics. And so we did, and the experimentalists have done a fantastic job, but we've been very surprised over the last 40 years to not have observed proton decay, and instead to have gotten better and better limits on the lifetime of the proton. So in light of that, I think it's worthwhile to remember that in the standard model itself, the proton is actually exactly stable. And the reason is an exact discrete global symmetry that's enjoyed by the standard model fermions. Now, let me remind you, when you write down the standard model Lagrangian, the most general Lagrangian of the standard model fermions that's gauge invariant, you find these so-called accidental global symmetries, that you can independently rotate all of the quarks by an arbitrary angle and independently all of the leptons, baryon and lepton number global symmetries. And then there's this very interesting story we've learned over the last 60 years of gauge anomalies. You find that when you quantize the standard model, in fact, you don't get to keep all of that symmetry. And the only continuous symmetry you have left over, the anomaly-free part, is this baryon minus lepton number, when you rotate them now in concert with each other. And you'll find that, of course, in all the textbooks. But note that baryon minus lepton number does not prevent proton decay. the proton decaying to a positron plus a photon or a pion or whatever perfectly preserves B minus L. And indeed, that's what happens often in grand unified theories, which can preserve B minus L, but still contain proton decay. So what stabilizes the proton is that by virtue of the Standard Model having more than one generation, there is an extra anomaly-free discrete symmetry. And it means that although U1 baryon plus lepton number is broken by the Standard Model, there's a discrete subgroup, a Z6, 2 times the number of generations, that's exactly preserved. And if you've thought very much about baryogenesis, this might be familiar to you. Of course, we have sphalerons, which break B plus L, but obey the selection rule. You only exchange 3 baryons for 3 leptons at one time. So, of course, I'm not saying anything fundamentally new here, but I think that the benefit of pointing out the symmetry reason for this is that I think it's very well motivated to consider extensions of the Standard Model that respect this symmetry. Because at the least, it's a far better symmetry than we expected it to be. Okay. So in everything I do, indeed, I will make sure to preserve this symmetry that prevents proton decay in the Standard Model.
Symmetry still exists if you have biodimensional operators? Is this another content?
Well, no. So if you don't, you can write SMEF with preserving all of them, but if you don't choose to, yeah. So yeah, you absolutely can very easily go beyond the Standard Model and break this, and there's nothing fundamentally wrong with it. But it seems like a very good symmetry. So it's interesting to consider maybe keeping it as an exact symmetry. Good. So from the global symmetries to the gauge symmetries, I want to ask, what is the infrared gauge symmetry enjoyed by the Standard Model fermions? Now, of course, we all know SU3 cross SU2 cross U1, but just by virtue of what I was saying on the previous slide, baryon minus lepton number doesn't have any ABJ anomalies. And so that means that B minus L could perfectly well be gauged without any new matter charged under the Standard Model gauge groups. So then it's an empirical question as to whether it really is just an accidental global symmetry, or it's maybe a very weakly coupled gauge symmetry. And thankfully, the experimentalists have come to the rescue with these great fifth force experiments that say, indeed, there is not another light vector gauge bosons. If B minus L was ever gauged, it must be broken. So you might say, okay, great, now we've landed back on the Standard Model, the familiar Standard Model gauge group, but not so fast. A discrete subgroup of B minus L is, of course, also anomaly-free and doesn't come along with any of these pesky massless bosons. So, to some extent, I think this constitutes an ambiguity in what we mean by the Standard Model. And I think, in general, it's an important question as to how much of B minus L actually is gauged. Now, a discrete gauge symmetry may sound exotic depending on your background, but it really isn't. This is something we could teach in a first year quantum field theory class. Just consider starting with the U1 gauge, and we look at the abelian Higgs theory, but rather than having the Higgs have charge 1, my Higgs has charge 6 now. Okay? This is a very elementary point, but if I do a gauge rotation by an angle lambda, the Higgs field then transforms as 6 lambda. So if I restrict my interest to rotations by 2 pi over 6, the Higgs is not charged under that discrete subgroup. So when it condenses and gets a VEV, it's going to break the continuous gauge symmetry, the vector boson will get a mass, but it can't break that discrete subgroup under which it isn't charged. So in the infrared, you legitimately have an unbroken discrete gauge theory. Now at this point you may say, okay, maybe you can do this, but who cares? I already told you there isn't a massless boson that comes along with it, and indeed there's no modification to local physics at all. But by virtue of having this extra discrete gauge symmetry, we have a new class of dynamical objects that appear in our theory, cosmic strings. These aren't that scary either. If you haven't seen them, I just go to my abelian Higgs theory and I look for solutions to the equations of motion that are independent of time and, say, the z direction. Now, of course, one such solution is to have the Higgs internally lie in the same angle at the bottom of its potential everywhere. That's the ground state. But there are these other solutions where the Higgs, as you go around transverse spatial infinity, the Higgs winds non-trivially around its internal manifold. And if that winding number k is non-zero, then by continuity, there has to be somewhere on the inside where the Higgs field vanishes. And indeed, you find, solving the equations of motion, that the Higgs is pushed back up to the top of its potential, and the symmetry is unbroken in a region of size roughly the inverse VEV. And since this is a gauge symmetry, the gauge field is sort of pulled along with the scalar solution, and you find a non-trivial gauge background. And in particular, you find that these cosmic strings have fractional magnetic flux running through them. B minus style magnetic flux, to be clear. And an important thing to note, whenever you have a fundamental magnetic object, be it a cosmic string or a magnetic monopole, the magnetic charge, or flux, is always inversely proportional to the electric charge. And this is very interesting because then when you have scenarios with both electrically and magnetically charged objects, the factors of the gauge coupling can cancel off, and you can find effects that are very far from free field theory, no matter the size of the gauge coupling. And that's going to be a theme in the rest of my talk. Good. What is my next slide? Ah, good. And so, yeah, in particular, the first such example, well, so the cosmic string, we might have some tube out there in space with some magnetic flux flowing through it. That's really an idealized solenoid. And so you have legitimately an Aharonov-Bohm effect. You might have thought that the Aharonov-Bohm effect required a massless photon to sort of mediate it, but it doesn't. All you need is an unbroken gauge symmetry in the infrared. So indeed, we can do this sort of classic undergrad setup. You think about if you take a standard model particle and move it around one of these strings, it can pick up a phase. That's the charge times the magnetic flux. And for the reason I just said, that the flux is inversely proportional to the gauge coupling, this is generally a large phase. But more interestingly, and importantly for what actually happens in cosmology, you can do this calculation that Aharonov and Bohm actually did in their original paper, where you think about shooting a beam of electrons at the solenoid and ask what is the elastic cross-section per unit length. And you find that there is an enormous unitarity limited cross-section for scattering electrically charged objects off of this magnetic cosmic string. And in particular, this cross-section is entirely unsuppressed by any small gauge coupling or any large energy scales. The size of the string doesn't matter. Okay. So this makes it. This is an argument I think for generally thinking more about say B minus L strings in cosmology. But okay, at this point, okay, maybe there's these interesting effects, but you might say, these formal theorists always writing down these weird solutions to field theory equations of motion. Who cares? But because we live in a cosmology, you are guaranteed to form these in the early universe by causality. Right? So in the early universe, you go through this phase transition, U1 down to this Z6, and at every point in space, the Higgs field has to choose some angle to fall down its potential in. And very simply, that angle cannot be correlated over scales longer than the Hubble length, because signals haven't traveled longer than that. So I have here, I've drawn some two-dimensional slice of the universe, and I've just randomly assigned angles to different Hubble patches. And this is some sort of random walk process. You find that there will be closed cycles that are formed and cannot relax. And you get automatically topological defects in the early universe. In this two-dimensional slice, these are vortices, you call them. but you can think in the three-dimensional picture, these are places where the strings pass through this plane. Good. So they're necessarily formed. But at formation, there's roughly one long cosmic string per Hubble patch. So if that was the end of the story, then there's no way that every lithium nucleus in the universe is going to hit that one cosmic string. But it isn't. These strings have really interesting dynamics. And so let's ask, so I've tried to draw here, that this is necessarily a three-dimensional phenomenon, so apologies for my drawings. I've tried to draw strings coming in and out of the blackboard, zooming in at the point where they will cross. And the question is, what will be the final state of such an interaction? Okay, and there's this really interesting phenomenon. We're going to first warm up by looking again at a spatial slice, a 2+1 dimensional theory, and ask about the scattering of identical vortices in the 2+1 dimensional abelian Higgs. And in particular, where I'm going to go to the supersymmetric limit because this is the only place I know how to make an analytic argument, but I'll show you that numerically this behavior is seen to occur far away from the supersymmetric limit. But in the supersymmetric limit, there are these really nice theorems that were proved in the 80s that you can understand the motion of solitons in real space by instead looking at their motion geodesics on the moduli space of solutions. So I'll just look at the very simplest moduli space. I have two vortices. The only coordinate on the moduli space is the displacement between them. So locally, the moduli space is just a plane. And I want to ask what happens when they collide. And so that's a trajectory, like this pink line, going toward the origin. And again, of course, your intuition from free field theory is that most of the time they'll forward scatter. They'll just go straight through, following a red trajectory. However, even though these are large semi-classical objects, they're actually quantum mechanically indistinguishable. So the moduli space, we need to do a Z2 identification or quotient because a configuration of displacement R and of minus R are exactly the same. And so when we do that identification, it turns what's locally the plane into globally a cone. And in fact, it does get rounded off at the top. Okay, and so now when we ask about this trajectory, the naive trajectory of just forward scattering would be a trajectory that goes up to the top of the cone and then turns around and comes right back down. So it's obvious that actually what will happen is you'll go up the cone and down the other side on this blue trajectory here. But when you unfold that back to real space, that is this 90-degree scattering. And so it's a fact, and I was amazed to learn this, and surprised it's not talked about more. It's a fact that these vortices always collide, and whenever they collide, they undergo non-trivial 90-degree scattering, right-angle scattering. So I think that's really fascinating. But it's useful for the question that I really want to ask, which is about what happens to these cosmic strings, because I can consider the configuration of these cosmic strings on different planes. And so if I take this horizontal, roughly green plane, then the string fluxes go through that plane in the same direction. So on that plane, the configuration, the interaction looks like vortex-vortex scattering, what we just saw, and you have to have that 90-degree scattering dynamics. Whereas, if I look on this red plane, the two fluxes go through in opposite directions. So on that plane, it looks like vortex, anti-vortex annihilation. And afterwards, on that red plane, you shouldn't have any zeros of the Higgs field. You shouldn't have any strings passing through it. So it might take maybe later offline, a few minutes of staring at this to really convince yourself. But in fact, the only end state that's consistent with these various 2 plus 1 dimensional dynamics is that the strings always intercommute or reconnect or exchange partners. There's lots of different phrases people use in the literature. But you always have these very non-trivial interactions. And in particular, when a string crosses itself, it will chop off a closed loop of strings. And these are very important because a closed loop can then oscillate and emit gravitational waves, and so dissipate energy from the string network. And so this is what makes, in my opinion, makes cosmic strings the most interesting sort of topological defect, at least cosmologically, because with either monopoles or domain walls, we essentially know that there aren't any around now. They would have overclosed the universe. They can't be here. But because of these really interesting dynamics, the string network can dissipate energy and prevent itself from overclosing the universe. And in fact, you find a so-called attractor solution in scaling that the strings per Hubble volume follows, as a function of the length of the string loop, just has a simple power law in terms of the loop over the Hubble distance. So any individual string, of course, it's undergoing some complicated dynamics. It's reconnecting and intercommuting and shrinking. But statistically, whenever you look at the string network, you look at a Hubble patch, it looks statistically like something like this. And the only thing that changes is how big the overall scale is. Okay? But you end up with, in particular, an enormous number of small strings. It's sort of interesting. Joe Ploczynski says some interesting words about this. You have power going to small scales. And so G mu here is the tension, roughly the Bev squared times over the Planck mass squared. And so in particular, for relatively light-ish strings, you get an enormous enhancement in the number of strings of relatively small loop size. Okay, good. Now, the last sort of phenomenon I want to talk about is, good. We saw with the Bohm effect that because of some electric-magnetic interplay, you have an enormous elastic scattering cross-section. And it might be a natural question to ask, well, could there be some analogous inelastic effect, some electric-magnetic interplay that again is very large? Now, of course, the situation I'm most interested in is cosmic strings, but unfortunately that's seen quite little study. And so to warm up, I want to talk about the case of magnetic monopoles, which are an analogous, another sort of topological defect of a lower dimension. And here, in contrast, magnetic monopoles have seen tons and tons of studies starting in 1931 with Dirac. So we really understand at this point, have a good understanding of what's going on. And there's this enormously interesting effect, which you can see from the far infrared. And this argument is due, or this formulation of the argument is due to Schwinger, really very far infrared. I'll just look at non-relativistic classical electrodynamics, and I'll just write down the Lorentz force law of an electron moving in the background of a magnetic monopole, and just plug in the monopole field. And you find, with just a couple lines of vector algebra, that the conserved quantity in this case is not just the normal angular momentum, but contains another piece of angular momentum, which is roughly stored in the electromagnetic field. And it's something you could write down essentially just by symmetry, the product of the electric and magnetic charges. It points from one object to the other. That's really the only direction you have. But this is very interesting, some sort of angular momentum that's there even when everything is stationary. And in particular, it also poses immediately a severe puzzle. Because you could ask about shooting an electron at a monopole. And of course, again, your intuition from free field theory is that most of the time it will just forward scatter. But if that were ever the case, if you ever had any forward scattering, then the displacement unit vector would flip signs as you went across the monopole, and that would violate angular momentum conservation. So that can't happen. You find just from the infrared that any magnetic monopoles have to have non-trivial, inelastic scattering boundary conditions on their core that roughly pair up fermions of different chiralities so that the spin flip can make up for this difference in angular momentum in the electromagnetic field. Okay. Now, from the infrared then, from this perspective, this famous Kalin-Rubikov effect that magnetic monopoles catalyze, quote unquote, proton decay, is just that from the infrared, all you know is you need some inelastic boundary conditions. But when you start out, when you've gotten your magnetic monopole from a grand unified theory, like I said way back at the beginning, these grand unified theories don't respect the standard model of proton stability. They generically have proton decay effects. And so they can give a boundary condition that causes proton decay. And you indeed find an enormous scattering cross-section for a proton to hit a monopole and turn into a positron. And again, it's entirely unsuppressed by gauge couplings or the gut scale. Really, this is the unitary limited scattering given by the size of the proton. Okay. Good. So you can see it just from the infrared. Once Tuft and Polyakov write down the monopole, you can get some complementary understanding from the UV, where you recognize that the magnetic monopole is really a non-trivial background of the Higgs field, Higgsing your gut group down to some U1. And the Higgs is really a map from spatial infinity or the spatial sphere, I should say, into the internal sphere of the potential of the Higgs. And so, to some extent, you can say that the Higgs field sort of Higgses together these separate internal and external SU2 groups, and you find that all that's conserved in the infrared is the sum of the external angular momentum and the internal SU2 quantum number. And so from the UV, the Kalin-Rubikov effect is that when your grand unified theory puts quarks and leptons into the same multiplet, then when you're scattering, when you flip this internal quantum number, that relates quarks and leptons and can cause proton decay. And I should also say, as I said, we understand the magnetic monopole case comparatively better. We've been studying it for 90 years, but I'll note that there's still interesting work, especially because it's some of our friends, Chaba and Turning and friends. There's still interesting work on understanding this from a variety of perspectives. So it's still a really interesting effect and thing to think about. Okay, but as I said, my actual interest is in the case of cosmic strings, which unfortunately have seen very, very little study comparatively. And so unfortunately, I can't give you that really nice sort of infrared argument for why there must be this inelastic scattering. I suspect there should be such an argument in discrete gauge theory. Probably this program of generalized global symmetries is the right language to formulate it in, but I don't have it for you yet. So instead, I'm going to make use of sort of UV picture from this really nice paper by Wilczek and friends in '89, a few years before I was born. And their interest was in finding that same sort of Kalin-Rubikov effect of proton decay in a cosmic string case. So what they did is they looked at cosmic strings of some gauge U1 broken down to Zn, just like we have, and they have a leptoquark condensed on the core. to explicitly provide some mechanism to carry away charge off down the cosmic string. And so you have an interaction between the scalar that lives on the cosmic string core, which is a leptoquark here, and so it interacts with a lepton and a quark. And so you can ask about what happens when you send in a quark. What is the cross-section for it to come out as a lepton? And they do this really nice quantum mechanical scattering calculation. And they find, indeed, the discrete gauge background enormously enhances the cross-section. And in particular, when your incoming quark has maximal discrete charge, because in a Zn group, sort of the biggest you can get is n over 2. When you have maximal discrete charge, you're again entirely unsuppressed by the small scale of the string or by the gauge coupling, and you find again unitarily limited scattering, an enormous scattering cross-section for this inelastic scattering off the cosmic string. Okay, so I want to utilize this explicit calculation. My interest is slightly different. They, as I said, they want to look at proton decay. I want to make sure the proton continues to be stable, like in the standard model. So rather than having a leptoquark condense on the string, I have a scalar condense on the string that just breaks the approximate global B plus L down to the same subgroup that the standard model respects. And I need to introduce some scalars to communicate that breaking to the standard model fermions. So around the vacuum, this is an enormously irrelevant 12 fermion operator. But the cosmological case of interest has 3 protons delivered to the cosmic string in the nuclear potential well of a lithium nucleus. So I claim it's at least somewhat sensible for me to sort of shuffle these quarks and leptons into separate spinners for the 3 protons and the 3 positrons, in which case I have something which looks exactly like what Wilczek and friends did, and I can hijack their calculation, at least approximately, and find that, again, you have enormous scattering cross-section, and because 3 protons have charge 3 under this Z6 subgroup of B minus L, that's the maximal charge, and so again, you find a unitarily limited cross-section, not suppressed by gauge couplings or large scales or anything. But a strong scale cross-section for 3 protons to hit the string and turn into 3 positrons. Okay, so those are all the pieces of physics, and then it's a numerical question as to whether or not this can actually disintegrate an order 1 fraction of lithium. And so, as far as I can tell, the answer is yes. Now, I want to be very clear there are lots of theoretical uncertainties here. We understand, I mean, people have been working on cosmic strings for 40, 50 years, and after lots of argumentation, we understand, we agree upon what happens for relatively large cosmic strings. There's still some theoretical questions about the case of small cosmic strings, but I try to take a benchmark that I think is reflective of the state of the literature. And of course, on the previous slide, I didn't do any sort of principled calculation because I don't know how to. I'd love to. But I take some benchmark model that I hope captures relevant physics, and in that model, the symmetry breaking scale to have the right number density of cosmic strings is around 10 to the 8 GeV, but I really don't want to claim any precision here. But my purpose was just to argue that it's plausible that such a thing could occur at large enough rates to really affect the lithium abundance. And it's nice to sort of unfold into, on the x-axis, the tension of the cosmic strings, and on the y-axis, the time at which this disintegration occurs, because the constraints sort of factorize that way. This blue line, again, is my benchmark with the 10 to the 8 as that green dot, but you could imagine trying to do this anywhere in this plane. And as for constraints, there are universal gravitational effects of cosmic strings, which is what most cosmic string people have focused on, and very interestingly from stochastic gravitational wave background searches and microlensing, femtolensing, whatever it is, we have constrained the existence of cosmic strings that are quite heavy. And very interestingly, we're already constraining gut scale cosmic strings. So an important qualitative point there. But if we're not committed to a grand unified theory, there's lots of space where these cosmic strings could live. And on the other side, on the other axis, the CMB is a great probe of the early universe, so you probably don't want to get too close to the CMB, but there's lots of time between Big Bang nucleus synthesis and the cosmic microwave background where this could plausibly occur. And what's nice is lithium is only 1 part in 10 to the 10, so you don't really have to worry too much about what happens to these outgoing positrons. It would be hard to mess anything up unless you got very close to the cosmic microwave background. Good. So that's really what I wanted to tell you. Quite generally, I find it really interesting that cosmic strings can have these really non-trivial, non-gravitational interactions. And I think they haven't gotten enough attention from particle physics cosmic string people. And in particular, I told you that B-L cosmic strings are, I think, especially well motivated and should really be studied. Even if you don't care at all, you don't believe anything I said about the lithium problem, I think B-L cosmic strings are a really interesting possibility to study. But as for the lithium problem, I hope that I've convinced you that there could plausibly be a real fundamental physics reason for the lithium discrepancy that you can actually believe in as a theorist. And I'll say again that I was really surprised to find this remarkably close to the standard model. And finally, to leave on somewhat of a light point, if you have a lead nucleus with 82 protons and it hits a cosmic string and 3 of the protons turn into positrons, you're left with 79 protons, which is a gold nucleus. So these cosmic strings literally perform alchemy. Okay, thanks very much. Happy to pick up.
Thanks a lot.
Then if you go back to your previous slide, what does direct detection means here?
Good. Yeah, so what that actually means is I was able to find one lithium direct detection experiment. Actually, this was just like a trial run. The full thing, unfortunately, didn't happen. It was in 2001 at Kamioka. And I've just done some very basic reinterpretation of their limits, which have sort of said that, after the CMB, if you tried to do this after the CMB, then the string network wouldn't have diluted very much by now, and so there would probably be too many around. They might have seen something.
So you're recasting a WIMP search into cosmic strings, is that it?
Yeah, I don't. Yeah, I suppose. Yes, yeah, sure. They were mainly focused on WIMPs, but I think they were really just looking at heat production. So my logic was that if a cosmic string came into their experiments, it would have produced at least the 3 positrons. And so I assumed that they didn't see such a thing and then was able to place it. But I should say, really, what probably the best constraint comes from something like Super Kamiokande, where you have tons and tons of oxygen atoms with more than 3 protons in there. As far as I've been able to tell from their papers, the searches they currently have running would explicitly reject these events if they are happening. And I'm not familiar with any work, and I don't understand physics well enough to know really the proper kinematics of cosmic strings in these direct detection experiments. So I have not yet been able to really direct them as to what sort of search they should do. But I mean, it would be very nice to understand that super K could in principle set fantastic limits. Yeah.
Probably should also look into the cross-section with the Baryon.
Yeah, good. So indeed, in the paper, I just relied on the lithium direct detector because that's at least sort of comparing apples to apples. Yeah, it would be really fantastic to understand how to sort of fold in the nuclear physics effect and how the cross section should grow with the number of protons. Indeed, that would be wonderful to know.
Any other questions?
You said that these guys produce gravitational waves when they're annihilating and things like this. What does that spectrum look like, and is your abundance large enough to give a detectable signal? So if you want to solve cosmological lithium, does it imply that you would?
Yeah, well, so the gravitational effects are just really proportional to the tension.
Right.
So indeed,
It's strongly on where you are along that axis.
precisely, and so indeed that does limit what the symmetry breaking scale should be. There are these nice searches with PTAs and things, and it's very you don't.
That's what's there on the gravity.
Yes.
Sorry.
Yeah.
So, just to see if I understood correctly, when you wrote that effect interaction for the Dyson destruction, there was some backcountry, but in the end it doesn't really enter, right?
Yeah. Yes, this is a very approximate.
Right, but even if you don't go into L, you expect that you is needed to matter because cancel.
Good. Well, so good. I think the gauge coupling effect should cancel, so it doesn't really matter how weakly coupled B minus L is. This is sort of a Yukawa effect. So indeed, if lambda was very small, you'd expect that the cross section would go down probably. I mean, really all of this is a crutch. And even I was happy to see these guys say much the same thing. You expect that just in the U1 to Zn theory, there should be some such effect like this. In analogy with the monopole case and because it's allowed by the symmetries. But unfortunately, still after 30 plus years, we don't know how to, I don't know how to give that argument. So this is sort of a crutch to say, at the least, if I also have this ingredient of scalar condensing on the string, then I can explicitly show that something like this happens. But I'd hope that really this is a property of the BF theory, of the discrete gauge theory of B minus L. But yeah, thanks.
There's a question to comment. No? Maybe as a mistake of code. So thanks a lot.
Yeah, thank you.
This is the end. I would also like to thank the local organizer.